All right. Welcome everyone to our new course, Contact Aware Control. Is elective, and it is a how would you call it? Author course, something like this. Like it is not from a textbook or anything. There's I designed it from the beginning, so that is why you can expect non-orthodox kind of like sequence of lectures, etc. Because there is no orthodoxy. It is a course that I invented. So I apologize in advance if some of the material, looks, it's like not as optimal as it could be. I will try my best to make it better. All right. Let me begin by just giving you a little bit of my view on why you need this course and like what the course is. So first of all, Contact Aware Control. Control, let's think about it as a key keyword here. All right. So control, you already have seen it in probably Introduction to Control, quite possibly in a few other courses. It depends on what your program was, control theory, stuff like this. And of course, this is the fundamentals, right? This is something that would be useful pretty much anywhere. And especially, you probably had a focus on linear control systems, right? Linear systems, LTI, maybe LTV. Yeah, so this was probably the foundation for your control knowledge. Now, if your education before that was related to robotics, then you also probably had courses such as Introduction to Robotics, maybe Fundamentals of Robotics, maybe Fundamentals of Robotics Control, anything like that, where you probably laid a little bit of a knowledge in terms of control and work with linkages, so multi-link robots, right? So specifically, you kind of were building towards understanding and being able to work with robot arms, right? Robot arms. But of course, also various other types of linkages like portal manipulators, parallel mechanisms, etc. But serial robots and robot arms specifically was probably the backbone. Okay, so you kind of built towards there. That's why you probably studied forward kinematics, inverse kinematics. Maybe you studied adaptive control. Maybe when you studied parameter identification, you also learned how to identify parameters in those lumped parameter ways. All of this is very useful specifically for series linkages, right? Of course, it is useful for other systems as well, but specifically it is often useful for series robots, serial robots. Okay. It is possible that you either studied or saw your friends study new types of courses, which are specifically designed for autonomous vehicles, like autonomous cars and drones. Those two types of vehicles became popular in our lifetimes, right? They're quite recent. Like autonomous cars became a thing, handful of years ago. And we have courses now that teach various types of topics related to autonomous cars. Often it is closely tied to computer vision, etc. But you also see quite a bit of MPC, for example, mode of predictive control, associated with those things. So there is a control and in various forms being taught for autonomous vehicles, right? What I'm trying to convey with this introduction is I'm trying to say your introduction to control was a basis, and then you had some branches, right? Some related to robot arms, industrial robotics, some related to autonomous vehicles. Now, with this course, I'm trying to grow a small branch towards a recent, like you can say, recent development in robotics, which seems to be going fast and strong. And that includes various robots that have active interaction with the environment. And in particular, walking robots, such as quadrupeds, robot dogs, bipeds, humanoid robots, but also a variety of robots that have to do something which requires acquiring and breaking contact, right? So in particular, you could think of manipulator which has to touch the ground as an example, right? As long as manipulator only picks up something, lifts it up, and manipulates it, if the picking up process is, designed well, you could avoid thinking about it as a contact with the environment. You can think about it as a just payload problem. Okay, but sometimes this is not what we want to do. If you want to write something that is, in a way contact with the environment. Again, there are ways to get around it. You could model it in ways which don't require you thinking about contact too much. But contact is still there. If you want to, for example, do tasks which require getting reaction forces in specific way, that is a contact with the environment. There are various things, but I think for us, the simplest examples, source of examples, which are immediately practical and not obscure, would be walking robots. So I will draw on them. But of course, we have plenty of applications outside of walking robotics. Right. Yeah. So we will draw on walking robots for our examples. Right. Now, why do we need specific course just to be able to talk about walking robots and let's say control with contact? What is so strange about it? Well, what is so strange about it is that in this contact, what you have is first of all a different type of entity called reaction force. In this lecture, we already will start to see what is interesting about it. So this lecture will be the first one where we explain what is going on. But we will do it for the first 2-3 lectures. So don't worry, we will get through this idea. Reaction force, quite a special thing, quite different from what you see in classical control, for instance. And we do not touch on it in introduction to robotics and other things like that. It does change how we control stuff. Okay, reaction force. Second, contact itself is a strange phenomena. First of all, it can be sustained. So, for example, if I have a wall and I contact it, I can keep this contact going, right? And then, in a sense, it will be very difficult for you to explain to me how this contact is different from, for example, the base of the robot being nailed to the ground, if we are talking about a robot arm, right? So sustained contact and the base of the robot being nailed to the ground, how are they different if the contact is sustained, right? Good questions. I'm not saying that they are not different in any ways. They are different, but this becomes something to think about, right? Then you can have a sustained contact, but in only some directions. Like, for example, we do not separate, but we allow sliding, okay? So again, different story here. Now with the sliding, what you can have is friction force, right? Force of friction, which you expect to act anytime any sliding occurs. How do you model friction? That stuff is from classical mechanics. We should know something about it, like the friction cones, the idea of dry friction being proportional to the normal reaction force, etc. Of course, and there is also an entire subject of tribology, which will tell you much more involved models for friction. All right, this is all good, but how do we introduce this into control theory? That is not quite as obvious as you would hope. Okay, so not as quite as obvious, especially when the friction is not always sliding friction, but sometimes is a stationary dry friction, right? What we call stiction sometimes. So the friction which is not equal to normal reaction force times coefficient, but less than or equal to, right? Suddenly something strange going on. And then finally, what can happen is contact can be lost. So you can lift up the contact. And then what you're going to do? It's something, again, happens. Behind each of those scenarios, there's a lot of difficult and interesting mathematics. And not only mathematics, but also practice. As in, I don't want to give you an impression that this course is more of a like appreciation of equations course. Okay, equations here were going to be very nice and worth appreciation for sure. Right, aesthetic admiration, etc., will be due. But they also dictate how we in practice interact with those things. If you look, for example, at how robots are being controlled right now, you will notice that quite often we deliberately avoid sliding, like skidding, for example. Like robots try not to skid, but sometimes they do successfully skid, right? For example, walking on ice is a famous example, used to be famous in the last decade, a walking robot on ice and being able to stabilize itself. But this is like more of a lucky chance. You can hear, if you know the videos which I'm talking about, it's by Rybert, and the robot was called Big Dog. Was a very famous video back then. If you hear Rybert talking about it, he'll tell you it was a bit of a lucky chance that it happened. But at the same time, most robots who do right now like walking, they try to avoid this type of situations. They try to avoid sliding. Why? Because there is something about friction which is still hard for us to control. And this is something we will see when we look at the equations. We will understand mathematics behind it, and we will understand the decisions people make about the friction. And you will be able to see which problems are still unsolved, which can be solved by you, for example, right? So the course is not simply like entertainment and math. It will introduce actual real problems that are faced by current robotics community. And for you as a user, as a programmer, as a developer, it will be key to understand those if you're going to work in this area. So I'm going to, from now on, talk, more and more freely about math. I will try to avoid defending every equation I present to you by real life examples. But keep in mind that all of those equations have relevance. Those problems are not mathematical problems; they are practical problems. In a way, the whole idea of contact aware in this course is a practical thing, right? It's not like in control theory, we're talking about equations. Control theory itself, you can think about it as a specific branch of differential equations, theory of differential equations. You could think about it this way. Contact-aware control is by definition engineering course. We bring in engineering problem, contact, and we make it, we find control answers for that. All right. Hopefully that was a little bit of introduction. I will delay the beginning no longer. We can start with the materials of the first lecture. But before, if you have any questions. Note that at any time during class, you can speak up. You can write in the chat if you want, but you can also just speak up. And I will be happy to stop and talk, like answer questions, etc. So don't hesitate. All right, so at any time during the lecture, please interrupt me and we'll discuss. Okay. Now, how this course will be constructed? First, we will try to spend some time introducing models, understanding how models work, because this is essentially a subject matter. Understanding models in contact-aware control is more or less the like the task of first importance. The models are not obvious, and understanding them is a requirement for controlling anything. So we are going to spend at least 2 lectures simply on models, and then we will move closer towards contact. And in those 2 lectures, first and second lecture, we are going to go from more general to less general. So today we are going to discuss a very general way to look at those models. We are going to look at ordinary differential equations and algebraic differential algebraic equations. Okay, ODEs and DAEs. This would bring some more abstract understanding of what is going on about the terminology we're going to use. And next week, we are going to look into the mechanical counterparts of these equations. So this week, it's going to be more about differential equations. Next week, it will be practical equations that we use in control of walking robots, any robots with contact. But this, what we are going to discuss this week is important, so let's pay attention to it. It's yeah, I promise it is important enough. All right, so let's start. So first, just a reminder what we are dealing with. So nth order ordinary differential equation, which is ODE. ODE stands for ordinary differential equation, can be written in such a way. So it's some function of nth of t, some function of t, of x, of derivative of x, of second derivative of x, third derivative of x, and finally nth order derivative of x. So this is an ordinary differential equation of the nth order. Okay. Just some function of those things. F. X of t here is a scalar variable. We could write all this in vector form, but you know, at the moment we don't have to, so I'm not writing it in the vector form. Now, normal form of this ODE, normal form, is different only in one sense. The nth derivative, this nth derivative, is now being on the left-hand side. Okay, so it has been expressed. So in the normal form, it has been expressed and is expressed as a function of every other derivative. So it is x, nth derivative of x is equal to some function of all other derivatives, including zero derivative. This is a zero derivative. This is the first derivative. It's n minus 1 derivative, and t. Okay, so general form is just a function of every derivative that exists in the equation. Okay, normal form includes one difference. The highest order derivative is being expressed. That is quite a difference, and we will see why it is important very soon. But for now, let's just appreciate that this is so. And in your studies, you have seen both of those, like linear ODEs. We often write them in this fashion, for example. Linear ODEs, we often write them in this fashion. In control theory, on the other hand, we love to write our ODEs in this way. So in differential equations, linear ODEs, we write them like this. In control theory, our usually first order ODEs, we write them like this. So both of them we have been using before. I mean, classical mechanics also love to write those differential equations like this, right? So it is not that one of them is better. We use both. Okay. Now let's see some examples. So here is two examples of ODE in a general form. So first is x dot plus sine of x plus 1 equals to sine of 2t. You could say this is not general form because the sign is on the wrong side of the equation. I would agree with you. This to me is not very important, on which side of the equality sign t is. To me, this is not very important, right? For me, what is more important is that higher order derivative is on the same side as other derivatives. Okay, so zero derivative here, for example. Like, so, yeah. All right, another example. X cubed, x dot cubed plus x is equal to 0. Okay, so two examples. Now, couple examples of the normal form. Here, x dot is equal to 2 sine t minus sine x plus 1. So you can see the similarity, right? And x double dot equals to minus x dot minus 2x. Now, let us move on. I think it will become maybe hopefully cleaner here. And let us remember linear ODE. So here I again allow myself this frivolous function on the right-hand side. It doesn't change anything for a general form to have it on the right-hand side. So I don't think that's a big deal. But yeah, we have this general form written like this. It is linear, so you have a coefficient times the derivative. Coefficient times the derivative. Coefficient times the last like zero order derivative. Okay, that is the linear form, linear equation, general form. Normal form here, very simple. You can just get it out of here. That will be, transformed like this, right? All we do is we just put everything to the right-hand side, divide by an, and we get this new expression. Now, the only occasion when it is not possible to do this transformation is when an is equal to 0, because dividing by 0 is not acceptable. But if it is equal to 0, then you just drop one equation, one as a rank of the equation from n to the n minus 1, because to be actually true, and you get your differential equation by with a lower order, and everything is great, everything is fine. So this representation will always be possible to achieve for a linear equation, right? There is no occasion to worry about it. It is always possible to go from general form linear equation to a normal form. That is just easy and straightforward. All right. Any questions so far? Right, no questions. So far, we were just looking at the normal form and general form, those two things. Now, let us, for a second, look at that was scale equations. Now let us look at vector equation. So what we would call it, matrix ODE or vector ODE, doesn't matter. So first order ODE in a vector form would look like this. So there is a vector function that maps vector variables to 0. Okay, to 0. So x is a state variable here. X dot is the derivative of the state variable. and this is some kind of vector function. It maps them to 0, which can be 1, 0, it can be multiple zeros. It doesn't matter. So f can be a function that maps Rn to, let's say, Rk. It's fine. For first order ODE, we would expect, I guess, Rn to Rn, but it doesn't have to. Okay, so this is the first order ODE in the vector form. Now, the normal form, this is much more recognizable. The normal form, it is x dot equals to f of x and t. That is what we have been working with in nonlinear control, in linear control, all introductory courses. That's just the equation of the year for sure. We have this equation almost everywhere, right? And this is just a vector form, first order ODE, so a system of equations, you can say, in the normal form. So that's it. Notice that those two equations describe mathematically the same object, like first order ODE, but normal form is a specific type of this equation. And while every normal form can be written in this way quite trivially, how do you do it? You just write dx dt, right, minus f of x t equal to 0, and here you go, you have a general form. So this transformation from normal form to general form is completely trivial. But the reverse transformation from here to here, that is not trivial at all. This is not trivial at all. We could try to do it, and let us try. If equation 9, if this equation is linear with respect to x dot, if this is linear with respect to x dot, which can happen, we could transform it in this way. So what is it? Basically, what we do here is, let me clear everything and show you. If f is linear with respect to x, what we can do is we can rewrite it. Like if it is linear with respect to x, it means that we can rewrite it as something like this: m times dx dt with respect to x dot, of course, sorry, plus f of 0 x t equals to 0. We could always rewrite it like this if it is linear with respect to dx dt. Why so? Well, we said it is linear, right? So this part is clear. This is a linear part with respect to dx dt. And why is this? Well, if it is linear, that means that we could always get the linear part out of this equation. And if we substitute here 0 instead of x dot, it would be the same as getting rid of this linear part. Right? So we could always rewrite it this way. And from here, we can always express dx dt by transferring this to the right-hand side and inverting matrix M. So M inverted minus from transferring f to the right-hand side. Here's f. Here's this 0 substituted here. All right. So this is what we got. What does this signify? What signifies is that we could indeed get from here to here always as long as first this equation is linear with respect to x dot, and second, M is invertible. M is full rank. If M is not full rank, we cannot invert it here. So this would be nonsense. Second, if it is not linear with respect to dx dt, we have to find some other method. Maybe it is possible to do it, but it is not possible with this method. So if f of x dot x t is linear with respect to x dot, then we could transform it into the equation term. All right. All right. Notice that now there is quite a bit of a difference between this, for example, where we simply divided by an. That was it, right? That was quite easy. And what we had to do here when we basically trying to find M, which is a Jacobian with respect to x dot, right? Have to invert it. We have to do this awkwardness. Quite a bit of a difference, but still doable. The only difference is caused by the fact that it's multivariable. Like before it, we dealt with scalars, where inversion is trivial issue. Here we deal with vectors, where inversion no longer is a trivial issue. All right. But yeah, we're still working with this equation with which we started. Normal form versus general form. All right. And we just noticed that it is more difficult for vector equations. Okay, let's move on. Hopefully we'll see why we needed all of this. Now, I will introduce a new object. We call it differential algebraic equations. DAE. DAE, differential algebraic equations. And they are, in general, written in this way. Okay. Notice exactly the same as ODEs, exactly the same as ODEs in the general form. So differential algebraic equations in the general form look exactly the same as ODE in the general form, but this matrix M is not going to be even if so this matrix M is not going to be invertible if x is if the equation is linear with respect to x. If the equation is linear with respect to x. If the equation is linear with respect to x, it is still not going to be invertible. Right? Okay. I will avoid for now the case when this equation is not linear with respect to x dot, because in practice for us, for robotics people, we always will be blessed by equations which are naturally linear with respect to the highest derivatives. So we are not going to deal with difficult functions containing x dot. But yeah, the big difference here so far for us is that this matrix is no longer invertible. Okay, no longer invertible. No longer full rank, you could say. It can be rectangular. It can just have a rank deficiency. Any of the two. So I've write it as determinant of M is equal to 0, but it doesn't have to be square. It doesn't have to be square. Yeah. Okay. So this is what we call differential algebraic equations. So far, the idea of algebraic is not clear. Why do we call them differential algebraic? That's not clear so far, but it will be clear in a bit. All right, let's look, I guess, at examples. Here are a couple examples of algebraic differential equations. So here we have x1 dot plus x2 dot as x1, x2 plus sine of t equal to 0. Okay. And here we have x1 minus x2 equal to 0. This is algebraic differential equation. Why? Well, let's compute m for this equation. M for this equation will be equal to 1, 1, and 0, 0. Correct? Pretty sure that's correct. So the Jacobian in front of the highest derivatives will be equal to 1, 1, 0, 0. You can tell that the determinant is equal to 0. You can tell it by observing that there is a row of zeros. Or if you remember, determinant is 1 times 0 minus 1 times 0. So 0. Okay. So this equation is our algebraic differential equation. Differential algebraic equation, DAE. Okay. All right. Differential algebraic equation, apparently by definition. Now, let us look at it for a second and notice that the name actually makes sense. The name actually makes sense. Why? Well, because you have what looks like a differential equation here. And you have something that looks like a algebraic equation here. Second equation looks like algebraic equation. Doesn't look like a differential equation to me. Does it to you? So it is a mix. It's a mix. We have differential equations and we have algebraic equations. That is the problem. That's the problem. That's why we call them differential algebraic equations. Oh, why is it significant? Why is it significant? Because how are you going to solve it? Let's say you want to just differentiate it using Runge-Kutta, like ODE int, ODE 45, any of this. How are you going to do it? You would want to express x1 and x2 as functions of state variables, right? But you cannot, because M is not invertible. Like this M matrix that we had above, 1, 1, 0, 0, is not invertible. So you cannot express x dot as a function of everything, right? Like you can't. So somehow you cannot hope to solve this equation by expressing highest derivatives and then trying to solve anything. This whole exercise that we have been doing from the beginning of the lecture is not possible here. So you cannot transfer this into normal form. Okay. If you could, it would have been ODE. But since you cannot, it is a differential algebraic equation. Hope now the name starts to make sense somehow. Differential algebraic equation. Do you have questions before we move to the next example? All right, no questions. Let's look at the next example. Here, let us see if this is a DAE. M would be equal to, let me move this a little bit down. It would be 1, 1, and here it would be, second row would be 1, 1. Okay. What is the derivative of this? Determinant of this matrix? It would be 0, right? Because determinant is, there are two ways again. One way is to say determinant is 1 times 1 minus 1 times 1, which is 1 minus 1, which is 0. Another way is to say two columns are the same, exactly the same. So they're not linearly independent. So determinant has to be 1, or it have to be 0. Two ways to achieve the same exact result. All right. What does it mean for us? It means for us we cannot possibly express x1 and x2 as functions of independent of like x and whatever else. Okay. We would want to, but we cannot. We cannot. If someone doesn't believe me, try to express x1 and x2 and see if you manage. Right. Another way to think about it is this. What if we get this equation and subtract it from, let's say, this equation? So we subtract the first equation from the second. We can do it because they're both equal to 0. So nothing changes. 0 minus 0 is still 0. So the second equation then becomes x1 plus cosine x2 equal to 0. And notice that this new equation is algebraic. So this is why, again, the name makes sense. We, by simply, adding, subtracting, etc., we achieve the algebraic equation. So we now can solve, for example, first equation and this new equation, right? And it will be equivalent system. And they would be algebraic differential and algebraic. So that's the situation. That is the situation. That is the situation. Good. Do we have questions about both of those examples? Okay. No, I guess no questions. Then we'll move on. So this is what differential equations are. Differential algebraic equations are. Notice again, I'm talking about only linear equations with respect to the highest order derivative. Okay. Now, let me introduce a different type of differential algebraic equations. Now, this is a differential algebraic equation in the normal form that is oxymoron, right? But normal form with algebraic variables. Okay. Here how it looks. Here is the equation in the normal form. All right. But there are some variables here, lambda, which are not differentiated. They don't have a derivative. And there is additionally this equation here. So lambda are called algebraic variables. And this, let me use it like this. This equation g of x and t is called constraints. So this is constraints. Yeah. So let us look at this equation, what we see here. This is quite a beast, quite a beast. First, it looks exactly like normal ODE, normal form ODE. Looks exactly the same. But this is something strange here. This lambda is a variable, but we don't know what it is. And it doesn't have a vector field associated with it. Like for x, we have x dot. So we know how x changes because we know what vector field associated with it. Like, yeah, we can simply differentiate forward or whatever. Like this variable is well behaved because we have this vector field x dot written out exactly, right? And yeah, so it's quite a normal situation for x. For lambda, it's not. With lambda, we don't know what it is. We don't know how it behaves. So it's algebraic variable. Okay. And now we have this equation. This equation, the difference is this equation doesn't have a derivative. It doesn't have a derivative. It is simply algebraic equations, same as before, algebraic equations, which do something. Now, let's just for a second assume that we don't have this. Let's say we don't have this. Then this equation above looks like an ODE, but ODE with completely bizarre variable lambda here. Why do I say completely bizarre? Because what is it equal to? How would you be able to tell me what lambda is equal to? Like it is equal to something, right? You have to solve this equation. You have to assume it is equal to something. But what is it equal to? You don't have any reason to assume it is constant. You don't even have a reason to assume you know its initial conditions. Like initial condition for ODE is x of 0. No one said anything about lambda of 0. So how you're going to solve it is a mystery for me. So without the second equation, the first equation becomes nonsense. Okay. Now let us, for a second, consider what happens when the second equation is here. Well, when the second equation is here, when this guy is here, let me change the color. So when this guy is here, what happens is lambda can be used as a factor that bends this vector field. It bends this vector field in such a way that this constraint is always satisfied. So for all time, this constraint is satisfied because x does not leave this manifold. Okay, this constraint we can also call it a manifold because it just describes some geometric shape in the Rn+1 space. If x is in Rn, then this manifold exists in Rn+1 because T, or you can say Rn, doesn't matter. So yeah, let's say Rn just for simplicity. Let's forget about T for now. You have this manifold, and X starts on this manifold. Okay, initial condition satisfies this manifold. Now, what happens is lambda makes sure that on no occasion this vector field X dot makes X leave this manifold. So like it goes along this hills and valleys, but let's say if it wants to leave, lambda will prevent it. That's how you can think about it. That's how you can think about it. In this sense, lambda can be thought of as reaction forces. So it's a reaction force that enforce this constraint. So if G is a constraint, equation of a constraint manifold, if you want, then lambda can be thought of as reaction forces that make sure you stay on the manifold. And this allows us to compute lambda, because now lambda can be computed. It is exactly what makes it possible for X to stay on this manifold. All of what I'm saying right now is a little bit abstract, and I don't give you all the details yet, right? But my main message here that this normal form of DAE makes sense, but only it makes sense only together. Like together, this makes sense. This individually does not make any sense. You cannot solve it. Like it is just nothing. Like it's not mathematical entities you can interact with. This is necessary because of lambda. Okay. On the other hand, if you exclude lambda from here, there is nothing. This constraint it can only be used to check if you indeed stay on this manifold. It cannot be enforced. So if there was no lambda, it couldn't have been enforced. So yeah, that's also important. Okay. Now, one consideration that can be maybe a little bit too much, but I want to say it because it is true. We could define constraints this way, okay? G of X dot, X and T. So the constraint didn't have to be only on on state variables. It can be on the derivatives too. This would be a differential constraint, what we call, but we could do it. But then the clarity will be lost, because then you would ask me, how is it different from general form DAE? How is it different from ODE? How, etc. Right? The clarity of the definition will be lost. Sometimes we actually do this because this type of constraint is, for one way or another, it is often much more useful than the constraint in the equation 15. So we will use this equation, this constraint too in the future. But for definition's sake, we'll always try to work with those equations. And then when we arrive to these constraints, we will reference them as a derivative of this, for example, something like that. Yeah, we will try to preserve clarity somehow through derivations, etc. You will see it. It's not going to be very difficult to understand what's going on. So there will be no model. But yeah, this we can think of as a definition, but we need to keep in mind that this is also possible. Okay. Questions so far? Okay, no questions. Good. Now, differential algebraic equation, linear in algebraic variables. Okay, linear in algebraic variables. What does it mean? Well, it means that you have some kind of Jacobian in front of lambda. So this is our ODE in a normal form. Right? You can say here is ODE in the normal form. Here is our constraints. Here is our reaction forces, what we call algebraic variables, right? And together they form DAE, linear in algebraic variables. Yeah. We could solve it by differentiating constraints and expressing x dot. So we can differentiate this equation here with respect to time. We will get this equation here. So how do we differentiate g with respect to time? Well, using a chain rule, right? So it would be dg dt is equal to dg dx times dx dt. You know, something like this, right? Plus dg dt, where this is like a strict derivative, yes, like partial derivatives. All of those are partial derivatives except this one. This is like let me write partial. Okay, good. And this is what we get. This is what we get. This guy here is Jacobian in front of x dot, right? And this is everything else which is not linear with respect to x dot. It doesn't contain x dot, basically. Yeah. Well, that's it. That's it. This basically, this is this partial g, partial t. Okay. But we can compute it also by just differentiating this and subtracting this part. Okay. Now, this equation here, Let me get rid of everything. This equation here is now, you can see instantly like this now looks like a model. Like you look at this and you ask me again, is it a general form? Is it a normal form? How is it different from ODE, etc.? But I could answer this, right? I could answer this. And how do I answer this? Very simply, I'll tell you. If the matrix M is invertible, remember the matrix M, like the matrix in front of highest coefficients. If this matrix is invertible, then it is OD. If it is not invertible, then it is DE, right? And it is not going to be invertible because L doesn't have a derivative in this equation. So lambda doesn't have a derivative in this equation. So if we rewrite it in some form that you like, whichever it is, like some general form, I mean, like collect everything on the one side, we would have identity in front of this guy, G in front of this guy, and 0 in front of lambda dot, because lambda dot is not in the equation. So we cannot expect, full rank mass matrix, what we call M matrix. So the matrix in front of higher order derivatives, because this guy doesn't have a first order derivative in the first place. Okay. That is the answer for this model. Okay, now good. This thing here is still equivalent to this equation, except initial conditions are slightly different. Like this equation is a constraint on the derivative of x. This constraint is a constraint on the state of x. If this is satisfied initially, and this is satisfied for all times, then this would also be satisfied for all times. Because this basically expresses how, the same constraint, but it doesn't tell anything about the initial condition. In practice, though, if you're going to use like some stepping method, something like a Rangikata, this constraint will not guarantee this constraint. There will be what we call constraint drift. We can discuss it in a later lecture. But yeah, they are in a sense equivalent with some asterisks. Okay. Now this equation, what could we do with it? So again, let me first qualify my previous statement. They're equivalent, except this needs additional conditions on the initial conditions. Initial conditions should be correct, but they should be correct here too. It is just that here it is explicitly clear what initial condition should be, and here it isn't. So here we should additionally consider initial conditions, but that's it. Otherwise, they're equivalent. All right. Now, what we can do is we can rewrite this equation here. Remember, it is identity in front of x dot g in front of x dot j in front of lambda, and nothing in front of lambda here. A lambda never included in the constraints. That's just a typical situation. Lambda is not part of constraints. All right. What we have is the same equation now rewritten this way. So I in front of x dot minus j in front of lambda, g in front of x dot, 0 in front of lambda. All right. Same exact equation. I just wrote it in a vector form. Matrix multiplied by vector. So that's it. The same equation. I didn't do anything here. Now this can be invertible. Okay, this is not even. Yeah, it can be invertible, and this depends on basically this being full rank. Like this matrix G times J should be full rank. Then it is invertible. And if it is invertible, then what we can do is we can solve it exactly. And here's the solution. how did I achieve the solution? Well, you could just do it by manipulations, or you can look up in Wikipedia exact formula for block matrix inversion. That is something you should do. You should look up exact formula for block matrix inversion 2 by 2. It is very useful. It's very useful. You should always try to look at it. As when you have 2 by 2 system in block form, always look at this equation. It's just going to help you. Yeah. So this guy here is just the exact formula for inversion of this guy. And notice it contains these blocks, which are inversion of G times J. So G times J have to be square and full rank. So square and full rank. That is quite a condition, But it can be possible for them to be, such that their inner product would be square and full rank. So why not? And not inner product, just product, right? Okay. So square and full rank. And then you have this exact expression. Now, if this guy, remember, it is basically partial G, partial T. So it is time derivative. Imagine if it is 0. Imagine if it is 0. So we delete this. One second. We delete this. Then we can delete all of that. And what we have is an x dot equals to this projector looking thing. This looks like a projector, right? Oopsies. This looks like projector times f of x. And this now is ODE. This is a normal ODE because it is written in the normal form and there are no algebraic variables. So it is clearly an ODE. And you have also lambda described as a function of, the same f, but projected into in different direction. If you remember something from, let's say, some kind of course on SVD decomposition, linear matrices, etc., projectors, you would recognize this as looking quite a bit like orthogonal complement of this. Quite a bit like, not exactly like, but there is something there. The reason they look very similar is because, that is the same block here and here, and this is identity minus this. So clearly, if there was a G here, and G can be here if we consider not lambda, but lambda times G, right? If we write it like this. G here, right? G here, which would be not a reaction force, but reaction force times Jacobian, right? Which is perfectly reasonable. Why not? Then we will have this matrix I minus this matrix here and this matrix here. So they would kind of like act as orthogonal complements to each other. Yeah, is interesting. This is just interesting algebraically to notice. But most importantly, when we see that as long as all of this is possible, and as long as this guy here is invertible for rank square, we could get rid of differential algebraic equation and make it into ODE. Okay. So this whole fuss about differential algebraic equations will come to a stop, and we can go back to our Ngekata and be happy. Okay. And what is the price? The price for this was that here we did the differentiation, which left us without explicit conditions on initial x. And here we assumed that this is square and full rank. That's it. Those two conditions allow us to go from DAE to ODE. All right, good. Questions so far? We have 10 minutes, so I would move on. But yeah, ask after the class. You can ask too, like in the chatting. So the fact that the matrix on the left-hand side is invertible, if it is invertible, right, would have implications. What implications? First, there exists one and only one pair x dot lambda that satisfies both differential and algebraic constraints. Okay. So basically, you cannot have multiple x dot, different x dot that satisfies this equation. You cannot have multiple lambda that satisfies this equation. Okay. The fact that you cannot have multiple x dot means that you would have a single solution. I'm oversimplifying it, like uniqueness of a solution of a differential equation is one of the most how should I put it, most interesting theorems, and they usually take a page to formulate, like a theorem for the uniqueness and existence of solution for differential equation. That is quite something, like a pleasure to just read those theorems. They're quite good, and I'm not trying to dismiss them. But basically, for those examples, you could say that uniqueness of x dot implies you would have one and only one solution. Yeah, in this case. Now, for with lambda, what it means is that you have one and only one reaction force that makes sure that you stay on the constraint manifold. Okay. Now, the second application is we can exclude algebraic variables from the problem. So even though they're there, we could exclude them. We don't need them, right? Like they exist, but we don't need them. We can forget about them. Okay, this is a very strong implication. A very strong implication. If we can forget about algebraic variables, not only does it mean that we can go back to ODE and solve ODE with all our powerful tools that we have studied before, it also means that we can replace them with a different algebraic variables. In fact, like anything else that would produce the same result would also work. So our model can be changed as long as we don't change the results in ODE, right? So the fact that you can exclude those variables from the problem is very strong. It unties your hands. If you don't need to know anything about lambda, which is often the case, you don't really care about lambda, then you can change your model in a variety of ways, as long as the solutions of the model remain the same. But yeah, so your what you do with lambda is not going to be as important, because ultimately it's going to be excluded from your equation. It's not going to influence the final ODE. All right, so those are implications. Okay. Now, here's a more general form of the same thing. It is more general because I added one more component, m of xt. M of xt. So this is a mass matrix, you could say, but only for x dot. Okay. So this whole thing, we can call it a mass matrix for x dot and lambda. But I wouldn't want to call it that, because mass matrix usually is in front of the derivatives, right? But it is some kind of a left-hand side matrix. But this is clearly my mass matrix in front of x dot. We call it mass matrix because it kind of like acts like inertia. It makes your equations go slower if it is big, go less or faster if it is small. Okay. like very similar to Newton idea of mass, changing rate of change of speed, velocity for a given force. Okay, the mass matrix, that's why. All right, so I can add a mass matrix here, and nothing will change. Like determinant of the mass matrix should not be equal to 0. It should be full rank. Should be full rank. And it should be square. That's important. That's important. We want it to be square. If it is not square or the determinant is equal to 0, then this is not like basically then we have to go back to the drawing board. We want in this expression here, like we still want it to be kind of like a normal form of a differential equation. So we want the left-hand side to be invertible in some sort of way. By the way, I could require this whole matrix here to be invertible, right? I could just require that. Could say, let us only consider equations where this whole matrix, big matrix, is invertible. But I don't want to do that. Like, I don't want to require that this matrix is invertible because, for example, this part here can be wide matrix. This can be a wide matrix, right? And it can have more columns than this matrix has rows, for example. And this may not be important. Like we could still, in some ways, we will see it in later in the course. We'll see this exact scenario. Under some conditions, we'll be able to say, well, we can replace it with the equivalent matrix, but with the correct number of columns, and then everything works again. So we don't really need this matrix to be invertible. Specifically, we don't have to have a unique lambda here. Like uniqueness of lambda here doesn't matter for us, as long as we can guarantee uniqueness of x dot. X dot should be unique. That is paramount. Yeah, and part of this requirement is that the determinant of m should not be equal to 0. Should not be equal to 0. All right, and this type of system that we look here, I see here, we will find it in robotics quite a bit. Like this is a very typical differential algebraic equation that we find in robotics. And this is next lecture. So next lecture, we will see exactly this equation. There will be slight difference here, I guess, slight difference here, but not, not very important. So you'll see when we get there. And I don't want to spoil the fun. But yeah, you will see this system next lecture, and it will be mechanical systems. So next lecture we go from all of those abstract things to concrete mechanical equations. And what I discussed today, you can find in books on differential algebraic equations. But those books are a little bit difficult to read. And I understand that it is, it's not necessary for this course. So I don't push it towards it. But what I'm going to discuss next lecture will be in literally every paper on working robots. It is what I'm going to next lecture. We will see equations that are everywhere. They're just absolutely ubiquitous. So we'll quickly dive into practical realm. All right, but I think that is it for this lecture. Hopefully we understood what is differential algebraic equation, what is difference from lit and ODE, and we hopefully understood how we can often transform it into ODE. Hopefully we understood the similarity between differential algebraic equation and general form differential equation. Okay, general form ODE. Hopefully we understood the difference. And seeing how those two, normal form, general form, can be transformed to each other. Maybe it was illustrative to differential and differential algebra equations being transformed to each other. All right. Oh, before we go, let me just let me see. Yeah, this last slide. So let me just give a couple examples here before we go. Differential algebra equations with variables. So here's an example. X1 equals to x1 dot equals to x1 plus 5x2 minus lambda. X2 is equal to minus x1 plus x2 plus lambda. And here's the algebraic constraint equation. So notice this is ODE. Those are constraints, reaction forces, constraint equation. Now here again, we have x1 equals to 10x1 plus 15x2 minus lambda 2 plus lambda 1 plus lambda 2. Okay. X2 dot equals to x1 plus 5x2 plus lambda 2. Okay. And 3x1 plus 7x2 equals to 0. Again, reaction forces and constraint equations. Notice that here G would be equal to minus 1 1, right? It will be a column vector. And J, right? J. So, and G would be equal to 2 and minus 1, right? And indeed, their product would be what is the product we are looking for? GJ, right? Let me see. Yeah, GJ. The product would be equal to GJ. What it will be? Minus 2, minus 1, minus 3. So it is invertible, square, so everything is fine. Here, on the other hand, J would be equal to minus 1, 1, and 0, 1. It is 2 by 2, while G is equal to 2, 7. So the product would not be square. The product would not be square. And that is, so it's not invertible by definition. So notice in the second instance, we could not invert the product, and that is, important detail, I guess. Okay. So in the chat. Okay. I will answer, Ahmad, I will answer your question just in 2 minutes. Okay. After I finish the technical part. Okay. So this is it. This is it for what I was trying to explain this lecture. Write me questions about it in the chat anytime you want. And that's it. I will stop the recording and then we discuss the matters regarding the points and everything else. Okay.